and welcome to the Microchip Is podcast. Join your host, Mike Maynard, as he learns about the technologies, products, and people that make Microchip Technology what it is today.
Welcome to the Microchip Is podcast. Today, I'm joined by Nitesh Satheesh. He's the Senior Technical Staff Engineer at Microchip. Welcome to the podcast, Nitesh.
Thank you, Mike.
It's great to have you on. Today, you're going to be talking about power packaging. But before we get into finding out why Microchip is power packaging, let's find a little bit about you. So can you tell us a little bit about your role at Microchip?
Sure. So Microchip is most well known for their embedded solutions, the PIC, if you remember, that goes way back, so 20, 30 years ago. What a lot of people don't know is that Microchip acquired many companies through its history. One such company was Microsemi, and through this acquisition of Microsemi, it embedded itself as a power manufacturer. So we have power devices. It could be IGBTs, it could be silicon MOSFETs, it could be silicon carbide MOSFETs, or gallium nitride. I am part of this power group called High Power Solutions at Microchip. I wear multiple hats. So we're sort of a company within a company in that, Microchip is a large organization. It's a corporate entity. But the way we manage new product lines or new products is somewhat like a startup. So I'm a senior technical staff engineer that's responsible for power modules primarily and gate driver boards. And I support the product line managers, our executives in making the right decisions, and also our customers to help them find the right product for their solutions.
That's fantastic. And today it's a little bit different because quite a lot of the Microchip Is podcast, we've been looking at, specific products and devices. But here you're going to be talking about packaging up products into modules. So why is it so important to get the packaging right when you're talking about power modules?
Sure. So there's building blocks, right? Think of them as Lego blocks. So in many instances, individual Lego blocks are fantastic. And these Lego blocks can be the 4-pin ones or the 6-pin ones. They're standard. Anybody can use them. But there's instances where it can get very complicated to use these standard blocks. And our customers would like more integration. And this integration could be multiple die. It could be multiple die of different kinds. It could be that the pins are laid in a certain way. It's to help our customers make their system better. And that's where power modules come in. And there's different flavors of power modules that could go into a car versus what goes into an aircraft versus what goes into an industrial motor drive that many of our folks never see. So that's why power packaging is important, but it's also very underrated in that nobody thinks about it until you do.
And that's interesting. So when people start thinking about it, they presumably quite often think about it because they've got a problem. I mean, what are the problems you get by not considering power packaging right at the start of the design?
So as engineers, you probably think about one of these 5 different aspects in power packaging, right? And I think the most important of them is your heat. So as power semiconductor devices, you generate a lot of heat, which could be due to losses in the system or otherwise. And it's your job as the design engineer to get this heat out of the system and the package effectively. So there's an aspect called thermal resistance, which is critical. And this is, I think, the number one option where engineers optimize. And then there's all the parasitics. So if you're able to optimize for parasitic inductance, parasitic capacitance, you could switch better. So most power applications are switching applications. So you're turning these devices on and off. And if you have non-idealities, these cause second and third order effects, which could impact your efficiency. It could impact, what other components you're able to use within the system, how expensive or inexpensive you can make the system, and so on and so forth. So, parasitic inductances and capacitances are important. And then there's a third aspect, which is, going back to the integration piece. So you want to shrink the system as much as possible. You want as much power as possible from as little space as possible. Now, this is a heat problem, but it's also how effectively you lay out the pins. So if you think about the Lego blocks, let's say where the pins come out for your other connections within the system are equally critical. So within the power system, that could be the gate drive. It could be the capacitor bank. It could be the output inductors or the output filters. So if you don't have an optimized layout, it's very difficult to connect all these up. And then this impacts your parasitics, and it's an iterative loop. And the final piece could be the isolation and creepage and clearance distances and such, which impact, let's say, some of the standards that these systems have to meet. So if you are familiar with communication systems, you have to meet certain EMI, EMC standards according to the FAA. Similarly, for industrial systems, we have to meet UL standards. For aerospace systems, you have to meet the AS9100, for example, which is a quality metric. But for rail systems, it's EN 50155. So there's many of these standards that you have to meet, which are impacted by your package design. And then finally is the reliability. So you want to be able to design a product in that could last you a few years versus just a few cycles. So reliability is another key important metric. And in some manner of speaking, these are all interrelated because if you try to impact one or optimize for one, you're going to see something else screw up. So you have to keep going back and forth. And that's why I call it an iterative process.
And presumably the reason you're producing modules is your customers, they have to solve this same problem, meeting the standards, getting the devices together in an efficient way. And so you're solving that generic problem for all your customers so they can then focus on what really differentiates their system.
Exactly right. So our customers really have expertise in the system. So they know how to make a solar inverter. They know how to make an EV traction inverter, for example. But it's our job to help them make that better. So if they were to use discretes, which they could, and in a lot of cases, if the system is under 30 to 50 kilowatt, you would use a discrete because that's the right solution. But, if you're in that gray area or you want to do something in a higher power, it makes the system design easier. It makes the life of the engineer designing the system easier by going to power modules. That's where we come in.
And it's interesting. I mean, I know power module is a bit more than just putting things in a box. Can you explain, how a power module is constructed? What's actually in that module casing?
Sure. But before I get into that, let me start from the very basics, right? So earlier on, I mentioned the power semiconductor device. So this power semiconductor device could be a silicon IGBT, or it could be a silicon diode, or it could be any material. You need to put this material on some sort of a substrate, and this substrate is what provides the isolation, which I earlier talked about. Now, this substrate could be brittle, depending on how thick it is or how thin it is. Now, there's power modules that, simply have this base plate and die, and is packaged up within a silicon gel and a plastic housing with pins coming off. But then for high rel applications where you have a lot of shock and vibration, or you have the necessity for better thermal transfer, you would include what's called a base plate. This base plate is thicker than the substrate itself, and it could be made up of different materials such as copper, aluminum silicon carbide, or something else. Now, these substrates are typically ceramic. Off late, there's a trend in organic substrates, but for power semiconductor devices, the most popular ones are aluminum nitride, aluminum oxide, or silicon nitride. And the silicon gel, which is coating the die once packaged up, is providing the insulation. And then to connect the die itself within the power package, you have, wires, but you can't have wires dangling around. So they're bonded between the die and to the substrate and then to the power pins that eventually bring the power and the signals out of the package.
And you're obviously putting die down rather than packaged parts into that module. So that's more complicated to do, right? But what benefits does it give to actually use that bare die?
So the bare die cannot be used as is for a couple reasons. So one, the thermal performance. So if you use the bare die, let's say as it is on a PCB, you're not going to get as much thermal transfer. The second aspect is the voltage. So the bare die without its packaging is unable to sustain the high voltages. So to operate at high voltage, you need to insulate, let's say, the gate to the source to the drain. And this insulation is provided by the packaging itself, but also the silicon gel that I mentioned. Now, there's also other module types or discrete types where instead of the silicon gel, you have an epoxy mold compound. This provides the same insulation, but it also provides some mechanical stability to the die in areas where there's high shock and vibe, for example. But you're unable to use the die as it is. Now, there's one other area where you could use the die within PCBs. And this is another area of expertise for Microchip, where we embed the die. It's called PCB embedding. And you could do power. I mean, we've demonstrated a couple of hundred amps and a few hundred volts within this type of packaging, but it's non-traditional. Such kind of embedded solutions typically go into sensitive applications such as medical. To give you one example, we do pumps for the heart, right? So there's something that needs to power that up. And this needs to be as small as possible. So you have to think non-traditional. And that's where PCB embedding, for example, comes into the picture.
That's fascinating how we've jumped from power all the way to pumps for the heart, and yet it's all microchips. So I love that, Nitesh. I mean, if we go back to power, I mean, obviously we've got a module, and you're looking to do quite a few different things. You're looking to get rid of a lot of heat, which presumably is going to require a fairly big base plate. But then you're probably looking to minimize the size, the weight, and maybe the cost. I mean, how does Microchip go about trading off these different features to get a module that's going to meet the needs of customers?
So it's like you going into a restaurant and looking at a menu. If the menu is too expensive, you're going to have a hard time picking the right dish. Similarly, for Microchip, we have a standard portfolio of parts that we typically start with. And then our engineers, our FAEs, support the customers and understand their needs and say, okay, here's what you should start with. But if I were you, I would optimize X, Y, and Z. So we have this capability of defining and creating custom and derivative products, which are standards off of our portfolio. So this makes sure that the customer has a starting point and then quickly can transition to the right solution for them.
So that's interesting. You're basically, giving people a standard menu, but then letting them order off menu if they want something special. So flexibility sounds like a really important part of your offering.
That's exactly right. So if you look at our history, Microsemi, and even before that, APT, and all of these companies, flexibility is how they became successful. And a large part of that was also the customer base. So Microchip as a whole is one of the largest suppliers to aerospace and defense, and Microsemi is no exception. So even in our power product offering, we provide a lot of solutions to our aerospace and defense customers. But, you have to tie that history with the reality of the market. Not every market or not every customer wants this, right? So some of them just say, hey, this is exactly what I want. Like the chicken tikka masala example we were talking about earlier. So
Mhm.
a lot of people know exactly they want that before they go to a restaurant. So, we have the solutions for them. And then there's some others who are trying to think outside the box. They're trying to push the envelope. And even if they aren't trying to do that, they're trying to reduce cost. So there's many different reasons for why customers may want to choose off menu. And, we make sure that we can support them, but it has to be a sustainable support. So we have to make sure that it's the right business model for us, number one. And second, it's the right solution for the customer. Because if you go too far off menu and you're the only one wanting that dish, it's difficult to understand if it's going to be good or not because you don't have a baseline.
I love that analogy. I think that's great, Natish. Just looking at what Microchip does, I'm interested. You design and you manufacture the model. So where is it that Microchip's secret sauce, makes a better product? Is it design? Is it manufacture? Or is it both?
Me personally, I think it's a combination of the two. So you have to have a good design, but you have to have a manufacturable design. Otherwise, your yields are going to be impacted, and then that impacts the cost, and then you're not able to sell any of this. So the design is equally as important as the manufacturing itself.
Interesting. So combining the two really makes a difference.
Yeah. And the secret sauce is experience. So our lead designer for power modules has 25 plus years of experience doing this for various customers. And, like when you're cooking, love being the secret sauce. I think here it's all about experience. It's about being there and having done that before.
That's amazing, and some serious experience there. You've clearly had this track record that's amazing in power module design. I'm interested, looking forward to the future. Are things going to stay the same, or do you see any trends in the way power modules are designed?
Wow, that's a fantastic question. So, again, going back to our history, I'll give you one example of aerospace and defense. So, you have drones that are taken off, literally. So, you have needs for drones which are different from, larger aircraft. So, you want lighter modules, for example. And these light modules need to perform the same way as the larger modules. So we created a whole line of power modules for drone applications, which are base plateless, very lightweight, very robust. And then on the other extreme, you have applications which require a high temperature packaging, high temperature die performance. So if you look at the examples of downhole drilling, so resources are key for any country, right? And in some cases, these resources are only available to us far below the surface of the earth, or in the depths of the ocean, where you could have high pressure, high temperature, and the environment is very critical. And so the equipment that you send down there to bring the resources up has to be able to sustain and withstand all of this. So, there's trends towards that. And then in our day-to-day life, AI is impacting us, right? But on the other end of that, there's something that needs to be powering these data centers, powering the AI GPU chips. And the larger the data centers, the more the power is required, and the larger the power modules that are required to continue to switch and support all of this. So miniaturization is important, but you're going to hit some physical limits based on the thermal performance, and that's where research into new materials that would allow better thermal resistance, better thermal transfer would allow miniaturization.
And that's amazing. I mean, you've talked about three very different applications there. It sounds like these power modules have an incredibly broad range of applications.
Yeah. So I mean, I could sit here and talk all day about applications, and I probably wouldn't cover everything. So we do see very varied set of applications, and that's what's exciting about my job, because I get to explore all of these different applications and try to find the right solutions for them.
Oh, that's awesome. Nitesh, it's been fascinating talking to you. I feel like there's a load more we could talk about on power modules, but we're limited for time. So from your point of view, what's the one thing people should take away from this discussion about power packaging?
Always design for your intermediate case. So I know historically designers have looked at worst case and designed for worst case, but that leads to over design. And when cost is important, when performance is important, over designing a system is like leaving money on the table, is like leaving extra chips on the table. So we're seeing that trend, and that's the one takeaway I'll leave the engineers with is, start to look at the intermediate case. I think, as suppliers, we're doing a better job of providing typical values and also characterizing for max values. So somewhere within that window is the intermediate case. And I think we need to start looking at that rather than just design for worst case.
That's a great tip for any engineers designing power systems. I love it. Nitesh, I'm sure people who are in the power sector, they're going to be interested to find out more about what Microchip does. What's the best way for them to keep up to date with Microchip?
So you would go to our website, and that's the best way. So microchip.com. So it's www.microchip.com/SIC. So that's where all the silicon carbide stuff is. So it's microchip.com/SIC.
That's awesome. Nitesh, thank you so much for your time and telling us why Microchip is power packaging.
Thank you, Mike. Thanks for having me.
Thanks for listening to the Microchip Is podcast. Please follow us on your favorite podcast platform to keep learning about the many technologies, products, and people that make Microchip what it is today. Look out for our upcoming Microchip Is podcasts and our new Beyond the Microchip podcast series.